считал ленивым. Ну и мы про работу, которая очень количество интересовалась.
Okay, thank you. Thank you for inviting me here. It's a pleasure to talk here in this audience. I will speak about my last work on some new difference questions for q-Virasoro conformal models. So the subject is more or less related to the infamous algebraic structure, which is this dear to many people Virasoro algebra. Okay, so it's an algebra. It can be thought of as a Lie algebra, really, because basically you're having a commutator. It's a linear combination, but then you should be careful with the definition of the central charge. The central charge should be then thought of as one of the generators of the algebra. Okay, anyhow, this is an algebra, and it has representations. It has many different representations, but one of the most important classes of representations is called V alpha, the Fermat modules. And these Fermat modules, they are classified by one complex number alpha. So for generic alpha, V is irreducible. And most importantly and beautifully, you can define something which is called co-product. This is a way to define the action of the algebra. I cannot go into details, so I will just use the words. This is a way to define the action of the tensor product on the tensor product. So to define basically how L acts on tensor W, where V is in V alpha and W is in V alpha prime. And indeed, it's almost as usual in the algebras related by the Leibniz rule, and here it's not much different. There is a very explicit formula which you can write.
And how is V acts on this tensor?
That is an excellent question. So one has to be careful, because naive definition with the Leibniz rule will give you that sort of the value of the C parameter on the tensor product is twice as much as the value on the Fermat module. And this is undesirable. We don't want that. So actually what we want is a clever definition, and there exists a clever definition which allows you to sort of take this C as just a numeric parameter. Then you forfeit the fact that this is a Lie algebra. This is no longer the case, but it's still an algebra, and what's remarkable is that C on the tensor product is the same as C acting on a single Fermat module.
Is it difficult to write down this expression for the action of
No, not really. I wouldn't attempt it because I don't remember it on top of my head, but it's very simple. It's something like, ln tensor 1 plus 1 tensor 2n, except here we have corrections. So the form 1 tensor, say ln minus 1 tensor z plus 1 tensor z n minus 2 z squared plus so. And then z is an auxiliary parameter. it's actually explicitly not symmetric.
But actually, it focus on the properties of three-form.
Yes.
Because if you act on the rate sitting on one point, and then by comparing the transfer to numbers.
Something like that. Well, it depends on how you think about it. Physically, yes. Mathematically, it's a definition.
Yeah.
Okay, so this parameter sometimes is called a fusion parameter. And this is the situation with the regular Virasoro. Now, as you have a definition of the action of the algebra and a product, you can define what's called intertwiners in mathematics. So intertwiners are really tensors of the form, for example, this is a 4-point intertwiner. And here you have four terminals. Four terminals. And you can define a tensor such which is invariant under the action of the algebra. What does that mean? Really, you can define the action of the algebra of such tensors for the reason that we have this rule that we just discussed. And then you can postulate a tensor, say, let's call it psi. And you can simply postulate a tensor which satisfies this.
What is the definition of
Psi is a tensor, some element of the tensor product of the four spaces, which is not just any element, but that which is invariant. For any maybe negative. Negative element. But actually for any element. Yes.
Is it just a theory?
Excuse me?
Is it causal theory?
It is causal. Okay, so this is the definition of intertwiners, and of course in physics we know and love them as conformal. These are functions. What are they functions of? Well, first of all, they are functions of alpha prime, and alpha prime. But secondly, they are also functions of these strange PC parameters, which have the meaning of fusion parameters physically. When you fuse to fields, to primaries, you gain a parameter which you have, which is the difference of the insertions. Double ratio is what you have fourfold, but when you fuse two fields, basically, two primary fields, and then the result is a decomposition in a difference of the position of the differences.
No, that's a regular part. It's the same part. Depends on. But here you have 4.1, this is SS2 invariant, therefore it represents on the double ratio.
Yes, that's
I think this is where that.
Yes, you can choose these four parameters to be 0. One says that there is a map between sort of a standard sort of physics operations that we do in conformal theory and mathematical sort of theory of representation theory of the algebra of Virasoro. There is a map. It's a little bit difficult, but it's more or less that. Okay, so that's the situation, and then you can study these tensors, conformal blocks or intertwiners, whatever you want to call them. You can study them mathematically and ask different questions. And one of the standard questions is, do these, so question, do these satisfy any interesting differential equations? And the answer is, of course, not always, but sometimes. So there is a very famous case when you consider 4-point, or any, actually not necessarily 4-point, for example, you consider 5-point or 6-point, and you can consider one of these parameters alpha to be not a generic complex number, as here, but the degenerate complex number. And it turns out that the degenerate, especially degenerate value, is related to the central charge. So the central charge is pointed by 1 minus 6 beta minus 1 beta squared. And the degenerate values are in some parameterization plus 1 and minus beta. And if one of the parameters alpha is specified by the degenerate value, then of alpha.
So just for this change,
Yes.
you're looking for the general field on some level.
Yes, yes. For these specific degenerate values, so answer, if one of the fields or sorry, of the representation parameters is degenerate, then indeed there is an equation which is very famous. Then there is what is called the VPZ equation. Well, if true, this is, well, at least the VPZ equation, but probably more. In fact, this is precisely the situation in my paper. I consider several degenerate representations, and I can make equations. Simpler, much simpler equations than GeoGebra. Okay, I will not write the VPZ equation because I'm sure that many people saw it, and because I don't have much time. What I want to do is and this is the main motivation of my work, I want to obtain a Q generalization of the VPZ equation. So, Q generalization of the VPZ. Looks like a basic question, so there is a Q generalization of the Virasoro charge. And probably there has to be some generalization of VPZ. And it turns out that this is surprisingly hard. So, to the best of my knowledge, until recently this was well. And many important projects sort of around the globe were related to finding this equation.
So, what is the censorship? What was the function?
the function is psi.
Sorry.
Yes, yes.
It's not just in the kernel of 11.
It's in the kernel of all the common kernel of all numbers.
Yeah, it's fine as some differential.
Yes.
For example, for points, second order differential equation, and you want some differential equation.
Yes.
But I did not get your input.
Yes. So in the standard case, what is PZ? PZ is a second order of PV, differential equation. What we want a Q generalizations. And it turns out that this is surprisingly intuitive. So this Q generalization is a relation to a class of problems in mathematical physics which are known as non-stationary difference equations. And let me, abstract for a second. So in integrable systems and more generally in quantum mechanics, you have a Schrödinger problem. And Schrödinger problem you typically have in two forms. One is called stationary, and what you have is h psi equal to psi. And this is not an accident, this psi is the same size as here. And this is stationary. But then there is non-stationary, when you have d over dt of psi, of t, which is some other psi, not this psi, is equal to h times psi. And of course, the two are related in a very simple way, namely solutions of the set are decomposed on the basis of the solutions of the substance. So you can here no. In my case, yes. Yes, but it's a generalization. You can consider time determinism. Yes, actually, yes. This is not an accident. Okay, anyhow, we can consider these problems not just for generic quantum mechanical systems, but for integrable systems. And for all famous integrable systems, of course, there's first formulation. Because you have Hamiltonian, this is a non-divided problem. You write Hamiltonian, you pose the problem of stationary Hamiltonian times the wave function is equal to energy times the wave function. No problem. But surprisingly, the second formulation is not available for generic integrable systems. Not that it's not available in principle, but it's not known yet. And for example, for the Toda system, it has been obtained very recently by Professor Shamil. In the
H is no, H is the same, right?
yes,
If H is no, what is the problem?
The problem is that if you write the naive second equation, it will turn out to be the wrong equation. It defines yes, but then the function psi of t that you will obtain will not have any direct relation to other objects in mathematical physics. For example, it will not have any meaning in the classical functions.
But it will not correspond to the wave functions in integrable systems, arranged integrable systems.
Yes.
It probably corresponds to some other integrable systems, not connected with the arranged one directly.
Not quite, because so if the system is Russian, not different but Russian, then there is no problem. You just literally naively do this second line and you're fine.
And probably also you will get q-Virasoro.
You will, for Russian. For Russian integral systems, you will. All is good. The problem first appears for the police, and that's
So you mean that when you have different situations, just the quantum mechanics doesn't work.
that's not the sure.
Or works in some different way.
All that I mean is that here H starts to depend on T, not trivial.
So the H that
H is adjacent, yes.
You should add some definitions of what you want, because naively you can do
but if you consider some systems, different situations, for example,
Yes, yes.
right? It has Hamiltonian H, which doesn't depend on that.
Yes, yes.
You can write this as a equation with this total.
Yes, in principle, but then
The non-stationary solutions to the non-stationary functions of topology.
in principle, yes, but then the resulting solution will not have any direct contact with the other branches.
So you want another Hamiltonian, which depends
Yes,
on
yes,
that.
yes,
But
yes.
then you will be total.
It will be something called a non-stationary Hamiltonian photon.
Non-stationary.
if you even explicit.
Yes, I will.
Also use differential keys. Also, if you want to incorporate a function, you need Hamiltonian, which is quite dependent on T.
Yes, absolutely. So let me then, I will stop explaining this general sort of nonsense, and I will move directly to the result. So, before that, how much time?
Well, usually like hour and a half. So
Yes,
we
yes.
have usually 1 hour more.
Okay, one more. What is conformal books or intertwiners of the q-Virasoro? I will write q-Virasoro algebra, it's very beautiful. It's a sum f n of t n minus t n plus n minus t n minus t n plus n. And these t's are, of course, proper analogs of the L generators here. And then there is this, which is something that you should think about as a generalization of the central charge. So it's very similar, everything is the same, more or less. Except now, instead of simple commuting, that you have this crazy sort of combination here, where the coefficients are given by a generator function. It's a formal function.
No, I mean, the first one.
Good. So in the limit, when Q is equal to R and T is equal to beta R, and when R goes to 0, you actually recover the definition of the ordinary Virasoro in the first one. It's a little bit more complicated than that.
But what is this space of the other? It's not the space generated by T in the diffuse sense.
It's not
We allow for infinite but we should subtract what will be the
It's not an associative algebra in the sort of sense. Because
yes, but what was the sense which is generated by traces?
the sense is that there exist explicit representations for T's, such that they satisfy this equation.
The fragment, not the algebra, but it's image.
Yes, yes. And this is a well-known sort of problem. And
in that case, the sum converges.
yes,
Does there exist elliptic Virasoro?
yes, yes.
Who is the name of central church?
T,
Small.
small t.
Also, Shamil, technical remark is that you can, in principle, replace these blackboards raised easy for you to write.
Sorry, what is L in the two formulas?
What is Ln?
L.
L is an index.
Which one is
It goes from 0 to infinity.
In the exponent, you probably have a sum over there.
and what is L? Then?
Good, and then here is also the same thing. Okay, so this is the definition of the algebra, and as I said, it's not literally an associative algebra. It's something more intricate.
What is the motivation of this definition?
The motivation is that the properly defined intertwiners for this algebra will satisfy, will be related to Nekrasov functions essentially.
But I guess this definition was invented before Virasoro.
Of course, yes. Okay, that's a good point how did they invent it. Well, I think Koller Reshetikhin had something to do with this. And his motivation was from conformal field theory. So in conformal field theory, you have to have the action of the Virasoro algebra on the theory. This is the definition of conformal field theory. And here, of course, if you define such a structure, you don't. This is not a conformal field theory. But it's something which Reshetikhin calls an integrable field theory. In the sense that even though there is no action of the Virasoro algebra, there are still infinitely many commuting currents. Something. And so, but this is, I don't really like, I can't pretend to be an expert in this particular question, but I think the right answer is that this is sort of the unique integrable deformation of Liouville conformal field theory.
Well, at least there is another deformation when you get masses angular. It's also integrable. It cannot be unique.
Fair enough. Fair enough. Well, okay, it's an interesting one.
Okay, but maybe, yeah, I'm not going back, I don't know how old that was, but still, what you need from this algebra, what is essential? Yes, so this algebra, I saw these formulas many times, but still, without your help, I won't be able to reproduce it. What is the analog of BPZ or whatever?
Well, BPZ is the central result that I'm going towards. But there are many things that you need to do first.
And what similar representations are similar to representations of Virasoro?
In many ways, they are similar.
Are they sort of Riemann modules or?
Yes, you can define Riemann modules.
But may I ask in the following way? You can try to construct the deformation of the Virasoro algebra just by writing Virasoro generators as polynomial vector fields.
Yes.
And replace the variables z and no, not the variables, operators z and d over z,
Yes.
which have Weiler commutation relation or Heisenberg commutation relation
Yes.
by q commutators. This can be represented.
I'm sure there is one way to derive this in this way.
Will it give something?
The problem is that there is also some, for example, naive way when you replace this by a Q number. And this is an algebra on its own, and people call it a q-Virasoro algebra.
It's not.
But it's completely different from this.
So
So,
this kind wouldn't come from construction which I mentioned.
probably it would, I think. No, this is a very natural algebra from many perspectives. Except it's not an associative algebra.
Wait, but you write completion relations. They will define an algebra.
Yes.
Disregarding the fact that it's fine. Just forgetting about this substances.
Okay.
Conditions relations, given generators as conditions relations, you can define an algebra if we require specific, otherwise how we have no definition.
Okay.
But you say it's not associated.
It's not a what?
You said it seems you said it is not associated.
It's not associative
But what was the definition?
for the only reason that it's an infinite sum. Because in associative
But what is
algebras,
the definition? Usually the definition is we take the three associative algebra with such generators and quotient by the isolation. But here, what is the definition?
the definition is really twofold. It's a representation of the algebra by explicit generators.
But the image.
The image, yes.
The image forms which algebraic structure.
It's a set of operators which satisfy this equation, and in this sense, it makes in this way it makes sense.
And that's all.
There is nothing better. Okay, no, there is of course something better.
But it's a set of operators. But the product of operators is associated.
Yes, but there is an infinite sum in the definition of the algebra, and an
But
infinite.
the sums converge.
No, but yes.
I think you don't understand. I'm not against. I'm trying to understand.
I'm saying a very simple thing. I'm saying that this is not literally an associative algebra.
But then what?
You can treat it in two ways.
Uh-huh.
First, you can think about this as a image, as we just discussed. And then second way is you can define sort of generalization of the class of associative algebras, which is what Rishetikhin calls deformed chiral algebra.
Let's speak about the image. Image is very good for me.
Okay, but then
additionally to this relation, there are some other,
yes,
right? Which we don't know, but
yes.
never mind. But the image of this quotation mark algebra
Okay.
is closed under the multiplication operator, or not?
Sorry, this is a little bit.
The image is a set of operators.
Yes, and if you
Linear
multiply two operators,
subspaces in space.
you have words.
Huh?
You have words. You have words.
Slow.
Slow. You have T1, T2,
Yeah,
T3
they're intersecting in some space.
in some spaces.
You have a linear subspace in the space of operators.
Yes.
Then, if this subspace is closed under multiplication operators.
Of course, of course.
then it's an associative pattern.
This is what I mean by an image. It's a
The image is an associative pattern, right?
but you cannot represent it with.
Wait, we're speaking about the image of something unknown, some representation, right?
Yes. That something unknown
This
is.
image forms an associative pattern, right?
It forms an algebra. I wouldn't say so.
But the product of the greatest is associative.
Yes,
There's
but the relations in the algebra. The relations in the algebra involve infinite sums.
Again, you consider subspaces in the algebra of operations. You could disclose under multiplication. Maybe it is not closed, I don't know. But if it is, it has to be associated.
Okay, are you saying that?
The question is, what is the representation of non-associative algebra?
What do you
Да,
mean by
есть
what do you mean by
Я еще не хочу говорить,
Отражение ничего не отвечает.
Ну хорошо, давайте я явно определю image. Let me explicitly define the image, and then we can solve this problem, I think, quite easily. So the image is defined by the following formula. Собственно, I apologize. For the result to be formulated, it's not really required that the algebra is associative, and it's a purely scholastic question whether it's associative. Which is an interesting question, but maybe I'm not prepared to answer.
You are writing now some kind of fourth representation?
Yes, that's it.
HT, why we have HT and A naught. So H is not A, yeah?
Also H minus Q.
Yeah, but A naught is not part of this H algebra.
Yes, I will define the algebra. here V is q to the 1/2 t with negative 1/2. And maybe something else needs to be defined. Perhaps Hn and Hn. Formal Heisenberg conjugate.
Don't they be realized by difference observatories?
Yes, in principle they can.
Then it is also
Perfect. I also need to define the extra generator A0. I think it has to be something. This is just a mistake because this is copied from paper of Polish and proper This is just H.
But in any case, each model already used for that.
Yes.
That's too much.
Well, basically, H's form a set of Heisenberg algebras, and then there is a distinguished element which is called H0, which is something. So this Q is not necessary for this formula, but it will be necessary for some other formula, and then we just write it here. This acts on the vector space.
What is beta? Some constant.
Beta is
How is it related to T?
yes, it's yes. Okay, so
This is sort of the form usual Heisenberg. Yeah?
Yes.
Added,
I need to present you.
Which not operator K.
Yes, I need to present you the image that we've been talking about. This is sort of the central construction of the paper. And for this, I need to present you a vector space with all of this acts on. And the definition is here. You fix a complex number, which is called sigma, and then what you do, you act on a vector space, F sigma.
Isn't it just a Fock model?
It is just a Fock model, of course. So basically, the vector space is the span of H's acting on C. So you have all the negative nodes acting on
And H with positive and Q this vector.
not quite. You have a condition that H HN acting on sigma. So the zero generator does not count.
Yes, you just condition you need to throw down in the first line.
Yes.
Then n is greater.
Good. Okay.
Just say that this is only for model. That's it.
Yeah. Okay. Okay. So this defines the vector space.
And so where is the image?
And the image is this.
А я тут только что
А вот что
в разных соседях означается через J докладно.
А сейчас что вы хотите сказать? Просто написано из некоторых явных Т через фоксский оператор.
Да, оператор.
Да? И вот что вы называете словом image? Это image или что?
Yes, yes. So this is the image. This image is solution to this equation if you wish.
So the statement is that if you define T in such a way, then it's more satisfying the sort of quadratic relationship.
Something like this, yes.
Why something?
Not literally, except for you have to be careful when checking this equation because it's infinite sum and it has to make sense. It does make sense, but it's a statement of mathematical rigor, if you wish, that it makes sense.
Do you need some regularization?
No. It's just you need to prove that whenever you're acting by this infinite sum on any particular vector,
So you convert it in the big set.
yeah, not only it converges, but you get a finite combination.
Your left is finite sum.
Yes.
If you look at this formula, both sides are formal power series in T and Q. If you consider the coefficient of any monomial in T and Q, is it polynomial?
I think it's a rational function. Everything is a rational
No,
function.
expand to the series in small t and q, both sides. So if you consider coefficient of any particular monomial,
Yes.
small t and q, is does it become finite combination of t operators?
Of T operators, of these?
Yeah.
Probably not. The only statement that I can sort of be responsible for is that when you act by the left-hand side on a particular vector, and any vector for that matter, you will get a finite vector.
Okay, then
Is it the same?
if you consider this representation, and if you apply these t operators
Yes.
to any h monomial,
Yes.
then the coefficient, what does it mean that this infinite sum has?
Well, you expand when you're acting by this exponents. What you do, you expand. So let's say you're acting on some sigma, you're expanding, and you have some number of positive generators here, some number of negative generators here, same here and here. This is not really important. And then you have to do the standard sort of weak theorem business. And it works in the sense that there is always a finite result.
Not really necessary. Simply e to the power positive a is a shift operation.
Yes.
Right? So you can write it in different way.
E to the power of positive.
H is positive index.
Yes.
Is differentiated with respect to variables which are h is negative, right?
Yes.
So e to the power
Yes.
differentiation.
In principle, you can.
Just a shift of the order.
Yes, that's the same computation.
Yeah.
But I'm only using this.
I mean, only technical model.
Yes, yes.
So if you have to take any vector, that means that you have finite amount of negative h, then when you act by this operator, you first shift just the values and then take some derivatives,
Yes.
and you remain with finite.
Yes, yes. That's correct.
May I ask about the general communication relations in the limit q goes to what? To 1?
Yes.
Or to 0?
Q goes to 1, that's the 1. Yes.
You told us that it becomes standard q-Virasoro.
Yes, yes.
But I don't see n cube.
Let me write the exact way how it becomes. So the statement is that in this limit, T of z is 2 beta z squared z. It's 1 minus beta squared divided by beta r squared plus some error term here.
And you take the limit r goes to 0.
Yes, yes. So in the leading, completely leading approximation, this is nothing. But in the first two leading sort of order, you recover the Virasoro algebra.
This q-Virasoro.
I saw this formula sort of many times, but I didn't check it.
What is z squared?
Z squared L is Z. L is the generating function for Virasoro, which is usually called T of Z. And this is just with extra factor, you substitute and from the relations, etc.
So it is like you take the limit, you take the limit of the commutator and divide it by r squared, right?
Yes.
No, that's, as I understand, not a simple representation. And then from this representation of T, you just get Feigenfuchs.
Feigenfuchs, sorry, what?
Feigenfuchs. I would say Feigenfuchs.
Feigenfuchs, yeah. Now already Feigenfuchs.
Okay, but let me somehow sort of make a positive statement here, right?
But just one question. The formulas on the right-hand side,
Yes.
does it make sense when q goes to 1?
Yes. You have similar formulas for
It's
standard.
just a presentation in terms of the free field.
Yes, yes. This is sort of somehow a Q representation in terms of free fields. Okay, so this algebra is a image on the Fock module of this relations. Right, so it's an explicit image for the generators T, which explicitly satisfies this relation, and it makes sense term-wise.
Once again, can I ask you?
Yes.
So if you take this the left-hand side of this relation, assume we don't know the right-hand side, and just look at the left-hand side. And
Okay.
try to apply it to any H monomial.
Yes.
Is it true that for a particular H monomial you have only finite many non-zero terms?
Yes, yes, that's what I was saying. And this is the only way, to the best of my knowledge, that this relation can make sense. Because otherwise, it's not an associative algebra, you have an infinite sum of the Well, to finish, I need to define a few more operators, but I think if I go at the same pace, I will not be able to present the main result. So I want to go faster. There is also another. Is there an eraser?
Вы можете ростом отметить, откуда мы? А то, знаете, как это самое, Василий квадрат, на следующем уровне.
Ну, формулу уже закрыта, невозможно.
Ну, то есть просто одним словом не сказать.
I can open it. I can review the formula anyway. If there is any comment to it.
It was a trick.
Alright, so there is these generators T. And there is a generator another one. It's called S of Z, and it has a very similar form to what's written there. Basically, it's called a screening charge. Well, yes, there is a statement that contour integral with respect to z of Tn, S of z, is vanishing. And then you can define a function.
In that form, yeah. What is the contour and why you should integrate?
Any closed contour in the context.
No other participants, I mean, or you suppose there are arbitrary operators and solutions, or no? Just that?
This is a local statement. That for a single.
The combinator is the derivative of Z of something.
Yes. In other words, you can define what's called a screening. This is a screening current, to be precise. And if you think about this operator as a single sort of entity.
So it means that the commutator does not contain the negative powers of the.
In usual Virasoro, that's what it used to be. Here, I probably yes. And then you define a function which is the main sort of function that we talked about.
Сумма альфа должна мне сказать, что
Sum alpha. There is a constraint. There is a constraint.
Sorry, может понять, да сколько?
Да,
потом
да.
же писать.
And what is V?
Excuse me?
What is V?
V is probably yet another object that I have to define. So V alpha of Z is something which is called the vertex. And here, all of them are similar to this formula T of Z that we have there. T, N, S, and V are objects of the same form that we discussed on the right-hand side.
Usually the Virasoro will have two types of screens, but there's only one.
V is also a sum of two terms, or V is like one of those.
That's easy to answer. It's one. And screening is also one. But T is a sum of two terms.
And when you go down to Virasoro, then usually in Virasoro case you have two screens. Because this condition is a quadratic equation and it has two roots. So what means that here we have only one? We have one or another one is not obtaining the limit or what?
Here you also have two. It's one is the sort of Q kind and the other one is T kind. And this is the same difference between sort of the two degenerate fields in the second level. One versus beta. Or whatever it is, beta versus one over beta. There's always this dichotomy.
How do you define that is the same, which is just the single part?
Well, S is found from the condition that it vanishes in this equation.
Yeah.
So you know T, and you find S from this condition, you find an operator.
Yes,
Vertex operator is a little bit trickier, but in any case, I just post-prove it. I get these formulas from Reshetichin's paper. Koller Reshetichin found these operators many years ago.
But actually, Virasoro have stated that it is a product of vertex operator or T has some particular single part, and here is the same. We have a product of T and V has
Basically, there is some nature definition. Probably we should just use the positive state.
Natural definition of what?
Vertex operator.
Okay. But it's some given manual free field construction is listed.
Yes. This is the definition of conformal.
This is the definition of conformal case.
And somehow it's also labeled by contours, right? So, I mean, in the left-hand side should be some information about values. In the notation.
Yes. So here there are several parameters. There are alphas, these kinds of parameters. But there is also, of course, parameters gamma. And there is also n, which is also a parameter, n. Well, as usual, conformal block depends on some parameters. Okay, so you can compute the conformal block because it is computable by the weak theorem, and it's more or less what you gain is an integral of the following form. So it's a product of two-point functions, where two-point function is basically just a matrix element. So what I denote by two-point function is just a matrix element.
So this is your statement?
No, it's...
Or is it looks like a weak theorem, but applied to something very strange, yeah?
Well, it's not very strange. It's a natural definition of a conformal block.
No, the upper, but I mean this lower, this multiple
Then I'm computing it. Computing it using the weak theorem for the Heisenbergs on that one.
So basically you just turn something, move something left or right, yeah?
Yes.
And then during this process you get these factors which are basically these 2-point functions.
That is correct, yes. And then in the end, what you get is a beautiful integral. You get an integral over gamma contours gamma 1, gamma n. Then there is a product which is the product of two-point functions between the screening charges. And then there is a product over the two-point functions with the vertex operators.
Just probably this is not important, but it should be also factor which doesn't depend on z, just a total factor which is the variance of.
Yes, which I ignore.
Okay. So, and just short question: is this what I mean? If we q generalize Jacobi numbers of it was quantum number, exactly this integral of representation.
Not quite the same, but it's more related, very closely. Because the two-point functions for the screenings
Yes.
are the measure with respect to which Q generalized McDonald polynomials are orthogonal. Is this what you're asking?
Q generalized polynomial, so it's another generalization from one.
No, Q generalized Jack,
Uh-huh.
which are orthogonal, which contain parameters.
So that's exactly that. So this measure is exactly that measure which corresponds.
Yes,
to-
that's the same measure. All right. So
What is phi?
phi is a very simple function. It's product from n from 0 to infinity, 1 minus q to the n. X. That's phi of x.
Oh, gamma is simple.
That's a problem. Yes. Okay, so this is the main object of study in our work. And with a little bit of effort, as you see, it's not all completely clear. There is some problem with the definition of the associativity here. And there is also a problem with, like, when you check, you have to make sure that it's active in a finite way. But if you do, then everything works. And then you can also define these auxiliary screenings and vertex operators, which do not appear literally in the definition of the algebra, but they are related to it. The screenings, I showed you how they are related. The vertex, I didn't show you how related, but they are also related somehow. And then, in the end, what you get is this great, nice integral, which is called q Fatiev. Integral. So, of course, this is a huge generalization of the well-known Fatiev formula for the usual conformal blocks. I'm sure everybody recognizes it. Okay, and now we are in the position to formulate the main results of the paper. Что?
Еще справа у вас еще есть...
Хорошо.
Наверх. Сзади точно не задели.
Хорошо. Denoting q to the alpha 1 as v to the negative 2 t1 t2 q, these are the Nekrasov parameters for this particular conformal block.
Кто у вас? Вот план Амосов по операторс.
Numbers are, so none of these are operators. This is just a clash of notation. So big T is just 4 numbers. T1, T2, T3, T4 are just 4 numbers. This is just an unlucky notation because everybody knows these T and I couldn't do anything with this.
Откуда такая куча параметров? 4T, 2T.
This is because this conformal block here is a 5-point. And so you have q to the, you have alpha 0, alpha 1, alpha 2, alpha 3, and then also you have n1, n2, and n3. And then you have alpha infinity, which is by this formula, somewhere here, but by this formula related to this.
So, okay, alpha 0 and alpha 4 is the same, yeah?
Yes, yes.
And you have n correspond to this intermediate channels.
Yes. So you have basically 1, 2, 3, 4, 5, 6, and 7 parameters. And you can see that there are 7 parameters in the board. In this parameterization, you can write the following equation for the main partition function. This is a sort of second order non-stationary difference equation. Non-stationary because you have a shift here in the parameter that is not shifted in stationary equations.
So psi is what was B on the left hand side.
Yes, that's good.
Ну, пси то же самое, что B для 4 точек. Для 5.
So how many axes is it?
Что?
On how many axes? So you have m point or m point function, and we'll see from here defined by this associative infinity. Yeah?
Yes.
So psi is correspond to which how many axes? How many points is it?
Psi is the case axes are usually situated at the positions 0, 1, then there is lambda over x, lambda and infinity.
I see. So lambda over x and lambda are two coordinates.
Yes.
Remaining, and you shift one of them. Yeah.
Yes. And then basically these three structure functions, A1, A2, and A3, are given by the following.
And who's gamma?
Gamma is a difference operator. That is the main difference operator that is defined by its action on the monomials. You can think about this as gamma is q to the d times d plus 1 over 2. Where d is x d of x. Yes. And then A1
And so, as you wrote, does gamma x only to the nearest function or till the end? Because from the formula, see, gamma which stays in front of A2 doesn't x further on A3 and on psi, or only on A2.
No, that gamma is, this is an honest composition of operators. So gamma literally acts on everything which is to the right of
On everything.
on everything, yes. This is an operator. So basically this is an operator of multiplication by a function.
So if in gamma is just a shift operator, so it's exponential of d operator
Yes.
d squared, then I would write down something like gamma times x is some factor x times gamma.
Yes,
But you have no gamma in the right hand side of this relation, yeah? What means that?
This means that this is an action, sort of. So this is applied to a function and then sort of evaluated at your exit. All right. So then this is a function that I want to write. And then there are similar formulas for
And who is phi big
phi big is another relative of this function.
or phi small?
Yes. Then A2 and A3 are similar. And this concludes the sort of main part of the talk.
But if you take ordinary Virasoro case, and then this second order this equation
Yes.
arises when one of their fields is degenerate on the second level. What is here an analog of degeneracy condition? Because it looked like you had an operator in generic position, yeah?
Yes?
So why is it important?
Well, one of these is degenerate, and actually the degenerate one is I think this one.
But does it mean that alpha 2 is special or?
Yes, one of them is special. Excellent. Yes, I forgot to write this. That's completely accurate. You have to put alpha 3 is minus beta, and N2 is plus 1. And this corresponds in this other notation to phi 1 is T over V, and phi 2 is so then the special field is alpha 3, so it's this one.
It's not just special external dimension, it's also special intermediate dimension. Right?
Yes, yes. There are two divisions. You're talking about the fact that
But N2 is plus 1.
N2 is plus 1, yes. In conformal field theory, this is somehow always the case, like when you have a degenerate conformal block, or a degenerate field, you have not just one condition, but two. So one of them is on the dimension, and then the other one is on the multiplicity of the screening charges running around the system.
So this is natural, yes.
If you take not a 5-point but say 4-point function,
Yes.
can you write down something similar like any sort of represent like equation?
Well, the 4-point function is too simple. 4-point function is
In normal Virasoro case you can, right?
yes, but it's a hypergeometric.
Yeah, it's hypergeometric.
And similarly here you get a Q hypergeometric.
So here you get this.
But this is the first sort of non-trivial case next after the Q hypergeometric.
And the equation is still not stationary
For the Q hypergeometric.
equation. Yes.
For the 4-point.
For.
Yes, yes.
But
Probably not. Probably not.
for
Because
stationary.
there are not enough parameters to talk about stationary versus non-stationary. Simply not enough parameters. There is only one parameter, and you have a shift equation with that parameter. That's it.
So it means station.
Probably yes.
No, like in 4 dimensions, you just have a single variable and you have a ordinary second order differential equation.
Yes, yes, yes.
So it's stationary in that sense.
Okay, so this equation is interesting from several perspectives. So now that I wrote it, at least partially, I want to say that, first of all, this is actually a quantization of different span basics. And this is somehow a result of our joint work with 7 Japanese co-authors, one of whom is Professor Shirishi. And this is quite interesting because Pendera 6,
Sorry, that's still a bit special case, right? Because in Pendera 6, all the parameters, all the external data are arbitrary, but here there's a condition that some of them is n. So it's not precisely the utilization of generic case.
I would say it's a generic Pendera 6.
But n is integer, so there's
N? Oh, okay, but it's a mild.
mild, but still.
Yes, n is integer, but then you can continue to generic n.
But how these parameters are related to parameters of the system?
I mean, this is external data.
In the system, you have
Yeah, this is just monotonous.
four is five external parameters.
No, four. One is special, one is degenerate, 4 generic. But in this case, there's like total sum is an integer, so it's not precise.
No, I'm asking from the point of view of the system.
In the 6 there are 4 monomers, 1 per point. So
This is the usual sort of problem in the approach from the perspective of Docent Fatiev. Because in the Docent Fatiev, you can only express your function in the case when the number of contours of integration is integer.
this is arbitrary, so this equation holds for any.
Yes.
And the size, I mean, in a sense, the order of this differential operator doesn't depend on it.
It doesn't depend on it.
Does it mean that you can just plug there n as just there is no
I'm sorry, I'm lost because who is n?
n is the total
N
charge.
is these parameters here, which have the meaning of the number of screening charges in the Fatiev.
You have three of them, and n is the sum of
Total n is the sum n1 plus n2 plus n3.
The basis of quantum is 3-dimensional, so you have to spread n divided into 3 groups, n1 and 2, and just such the sum of them is n, and so.
Okay, so this is just one sort of aspect of interest of this equation.
sorry, about, so you're saying about cube analysis, yeah?
Yes.
And so how do you quantize it?
Well, that's an excellent question. So you use the symmetry group. There is a symmetry group, which is, in the case of the difference from the 6, it's actually, as one of my Japanese co-authors found out, it's an affine D5. And then he used the symmetry group to rigorously quantize the equation.
But how, well, that's, it's not necessary to be a very clever Japanese scientist to know this fact, even I don't know it. But how to use this group to quantize it?
Well, how do you quantize? Honestly, I didn't follow his work, but
About the final
Группу симметрии, это 6 это 5.
а не квантовый.
Нет,
Я
она не квантовая просто.
Обычно.
Обычно это афинный D5, да? И это, ну, в общем, многие факты здесь есть, да? И уж японцам тем более. Но это же недостаточно, чтобы квантовать.
Но
Вы
вы когда спрашиваете, что есть какая-то проблема с квантованием, я просто не могу понять. То есть вы подразумеваете, что есть какая-то проблема с тем, чтобы проквантовать это уравнение, в чем она может состоять, я не очень понимаю.
Ну, я просто не понимаю, что это за слово квантование.
Ну, как обычно, построение системы операторов, которые там коммутируют, в пределе коммутатор превращается в...
В каких переменных? Кто канонические переменные у вас?
Ну, я так понимаю, что они как-то выбрали канонические переменные согласованным образом со структурой симметрии D5.
Ну, вот я вам могу такое вот сказать, что можно, значит, рассматривать это как вот этот самый Менделеве, как детерминизацию некоторой интегрируемой системы на кластерном модели. Там есть кластерные переменные, у которых есть естественное кластерное свойство. Вот вы ее квантуете или...
Ну, наверное, ее, я думаю, да. Но как бы лично я ничего не квантую. То есть, я отвечал вот за это уравнение совместной статьи. Но как бы то, что делают японцы, значит, во-первых, один из них квантует Менделеве, а другие как бы устанавливают связь между этим уравнением и
Уравнение в обычной жиросозе.
Простите?
Какой предел этого уравнения в обычной жиросозе?
БПЗ.
Но это же не Пендлевер 6.
БПЗ это не Пендлевер 6, да.
А как же? Это Пендлевер 6, там какой-то квантовый, там разностный, а предел-то.
Это получается БПЗ, а Пендлевер 6 получается в классическом пределе, получается уравнение Гамильтона Якоби, не Пендлевер 6. Получится, это не того, как бы аналог уравнения Пендлевер 6, а уравнение Гамильтона Якоби, Пендлевер 6. Да.
Сейчас, вы в классике говорите.
Ну да, я так правильно что ли?
Правильно.
То есть если
Нет, а на какую букву будет Пендлевер? Классическая.
В каком смысле?
Пендлевер экспериментная зависимость.
Ну да.
А вот X какой-то.
Да, скажите, можно написать, какой квантовый Пендлевер 6, которому уравнение отвечает.
Это уравнение является квантовым разностным Пендлевер 6.
Но это уравнение жизни.
Но оно квантовое, поэтому это уравнение на букву пси.
Да.
А классическое Пендлевер это уравнение будет букву У.
Да.
То есть, что здесь это будет? Говоря по-другому, я бы сказал, что уравнение, квантовое уравнение, собственно, Пендлевер 6, это должно быть аналогично Гейзенгеру. Уравнение аналогично вашему Шейзенгеру.
Должно
Вы
быть.
можете написать?
Не сейчас.
Ну, то есть у вас в тексте не написано?
Нет, я думаю, что это как бы это известно уже на данный момент.
уже раскрашены на
Ну
русский.
и вообще, Пендлевер уравнение в одной переменной, а здесь две переменные.
Да.
Как это?
Антон, еще раз, слышите, я говорю, по-японски, это уравнение Шрёдингера. Здесь t есть, dpt, dψ равняется d2 x в квадрате.
Это я понимаю.
Так а что ты спрашиваешь? Здесь две
Но
переменные.
Пендлевер одна переменная.
Ты слышишь, что я говорю, что надо взять соответствующее уравнение Гейзенгера. Ну а как ты иначе?
Пендлевер гамильтоновой системы. Ее можно писать уравнение гамильтоновой иконы. Если его прокомментовать, получится уравнение сценарного уравнения Шрёдингера. Вот это уравнение. Ну, в смысле,
наоборот, из Шрёдингера легко получается.
Ну, в смысле, классический предел уравнения Шрёдингера.
Да.
И вот эти две буквы.
А по идее, ну, насколько я понимаю, Шамиль меня поправит, что все, что ты хочешь, что это вот, ну, написать аналогично Гейзенгерскому уравнению, тогда оно будет похоже на, собственно, Пендлевер 6, и в пределе его должно будет давать. Да.
Ну, это, наверное, какие-то хорошо известные вообще факты, потому что я, на самом деле, не очень хорошо знаком с теорией того, как конформные блоки связаны с Пендлевер 6. Но это хорошо известный факт, что есть связь.
Известный факт, что есть связь, не одна, как бы сказать, это юник, но потому что есть две разные формулы. Есть, значит, одна формула киевская,
Да, это то, что я слышал.
а другая, это есть вот Леша Некрасов, там замолодчиков и
Лукьянов.
И Лукьянов, да. Они написали для классического блока связи. Это вот как бы две стороны одного и того же, но они связи немножко разные.
Но здесь теперь вот связь будет полностью точной, в том смысле, что как бы все квантовое, вообще все квантовое, все разностное.
А как это получено формула? Это, ну, то есть,
Эта формула угадана,
Проверенные прямые вычисления.
проверена и доказана после этого.
то есть,
А есть куда дальше, например, в Ливне какой-нибудь?
Есть. Значит, очень интересный вопрос, что будет в эллиптическом случае.
Что из этого есть?
В эллиптическом случае есть как минимум конформные блоки.
А там в случае четырехточки будет какая-нибудь эллиптическая или эмпирическая функция.
А в случае четырехточки там эллиптическая и геометрическая функция. Но она тоже чего-нибудь удовлетворяет, естественно.
Но она такая, там, если эти какие-то там f2,1 типа, то там какие-то f10 есть.
Нет, ну, есть же эллиптическая 2 в 1.
Нет, эллиптической f2,1 нет, в том-то и дело. Они там первые вот нетривиальные начинаются там, типа, я уже сейчас не помню, с больших всяких, там, типа 8,7.
В каком смысле эллиптическая 2 в 1 нет? Ее же можно написать.
Но она плохими свойствами обладает. Хорошими свойствами они обладают уже с большой шумировкой.
Это интересный вопрос, потому что здесь, я думаю, как раз возникнет эллиптическая 2 в 1.
Да.
То есть, может быть, она и, может быть, и не обладает таким хорошим свойством.
Нет, ну мало того, они там должны быть еще чуть сбалансированные. Там.
Да, нет, это правда. Ну, как бы там ни было, значит, вот есть такой конформный блок, есть такое уравнение, которое он удовлетворяет. Это уравнение обладает рядом интересных свойств. Значит, оно, во-первых, имеет отношение к квантованию в гневе, во-вторых, оно является q-деформацией уравнения БПЗ, и в-третьих, его следует понимать как нестационарное уравнение Шрёдингера для системы x и z.
А это можете объяснить?
Да, значит, ну это, значит, вот функция Некрасова, соответствующая вот такой ситуации, является волновой функцией, нестационарной волновой функцией системы, интегрируемой системы x и z.
На каких скольких узлах?
Простите?
На скольких узлах?
В каких узлах?
Ну, XZ это на узлах.
Тут понимаете, в чем дело? Значит, это вообще спиновая система. Но как бы, если вы посмотрите на это уравнение, в нем ничего спинового нет. Это уравнение многочастичной интегрируемой системы.
Ничего многочастичного нет.
Хорошо.
Один на это.
Но это двучастичная интегрируемая система.
Ну, то есть два узла. Я бы
Видимо, два узла. То есть, как бы, наивно это никакие не узлы, потому что это не спиновая, как сказать, эта система записана в такой форме, что...
Если какой-нибудь большой, то там можно и непрерывные переменные вести, или там ставить каких-то разных операторов.
Значит, я не видел эту систему в спиновой форме, поэтому я думаю, что правильный ответ — 2.
Скорее всего, там более масса.
Я имею в виду, что, значит, если вот в этой системе выключить параметры...
Вы имеете в виду следующее, что некрасовая станцума для этих 4 мультиплексов материи описывается спиновой цепочкой на двух узлах.
Да. И это как бы отражение этого факта некоторое. То есть это здесь.
Ну, она еще, кстати, Антон, плохо, потому что она на самом деле это неоднородная спиновая.
Ну, это уж наверное.
Наверное, точно. Иначе, ну, параметров не хватит.
А зачем такие самые параметры вводить? Это так вот неестественно, казалось бы. Да, Т1, Т2, Т3, Т4.
Это некрасовский параметр, нет, это на самом деле совершенно естественная форма.
Нет, некрасовые там были эпсилон.
Ну да, но это же как бы q некрасов.
Это не красок, а пятимерная. Пятимерная
Да.
уравнение, пятимерная приборочная связь.
Да. В пятимерном теории.
Собственно, краски. Там 4 массы должно быть, да, 2 эпсилона и кто еще? Констанция.
Да. Вот они все здесь и есть. Эпсилон это q и t.
А в исходных альфах оно что, хуже будет выглядеть?
В исходной...
В исходных альфах.
В исходных альфах, ну да, нет, оно тоже точно с тем же успехом можно его записать в альфах. Просто так случайно исторически получилось, что я написал Некрасова. Потому что с функциями Некрасова удобно работать на компьютере.
Это же Некрасовская станцума с дефектом, правильно? А вот в Некрасове есть такая вот техника там с этими, с тождеством Уорда таким, вот он там что-то вставляет, и у него получается какие-то типа такое уравнение, или типа Y-система. Это вот уравнение как нельзя вывести?
Ну, нет, как бы...
Ну,
Некрасовая станцума с дефектом это само пси, да?
сама пси, да. Ага.
Ну, скажем так, он не выиграл.
Не, я понял, ну в
То есть,
принципе...
видимо, там была какая-то проблема.
Мгм.
Я не знаю.
Понятно. Ну, то есть, в принципе, это ожидается, что это уравнение связано с этим?
С Некрасовой станцумой?
Ну, да, я понял, что оно именно вот должно выводиться каким-то таким же образом, наверное, да?
Видимо, да.
Понятно.
Вот, то есть это уравнение имеет минимум 3 интерпретации. И, ну, лично меня больше всего радует то, что это q-деформация ВПЗ. То есть, как бы, очень приятно, что можно знаменитое уравнение ДТЗ будет понятно. Ну и как бы связь с уравнением ТНВ тоже интересно. Я планирую в дальнейшем ее изучать и смотреть, как бы, может быть, это можно обобщить в какие-нибудь exception groups, так сказать.
Ну, сначала лучше написать для других людей.
А это не то же самое, что для других групп? Ну, как бы, есть же связь, да, что как бы разные уравнения ТНВ соответствуют разным группам симметрии.
Да.
То, что я здесь имею в виду, что можно Т5 заменить на там Е6, Е8, что-нибудь такое.
Ну, вы сразу хотите замахнуться. Но дело в том, что там выше Т5, там нет некрасовой фиксации. В этом проблема. Они же, зато они есть.
Ага.
Но это физически простой аргумент, который вы наверняка знаете. Вы за 4 мультиплируете материи, вы можете закончить их массу знать бесконечность. Но я в четырехмерности говорю, но тут какая-то аналогия.
Ну, естественно.
И тогда вы получите там низшие ТНВ, они там в одной там, такая группа растут, а в другой выпадают. Короче, там будет попроще.
Ну, понятно.
Вот. И вот эти группы, на которые вы ссылаетесь до 5, она будет проще. Там, меньше параметров и все такое. А вот что выше происходит, я на самом деле плохо себе представляю, потому что там ситуация, по-моему, более сложная, и во всяком случае там ситуацию Некрасова, по-моему, в качестве решения не лежит. Ну, нет.
Понял.
Еще вопросы?
Что-то можно сказать про деформацию линейной задачи? Вот если мы говорим квантование линейной, что происходит? Что
линейные задачи, в смысле, в каком-то
тем есть, там линия появляется как условие изменодромности линейной задачи.
Допустим.
Ну, а вот мы проквантовали это. Этот язык квантуется, задача, я не знаю.
Нет, я ничего не могу сказать.
В Штихина была какая-то работа на эту тему. Трудно читаемая. Давно.
Плюс, ну, тут, наверное, что вы говорите, я не говорю, эта линейная задача, она, собственно, не дает, она же что-то дает вроде Шрёдингера.
Я просто поэтому спрашиваю, я не знаю, может это другой Шрёдингер, я не могу создать.
Но это еще разность, там с этим, примерно, куски. Спасибо.
Спасибо.
Вы сейчас куда-то уезжаете, да?
К себе?
А?
Нет, я сейчас к себе возвращаюсь.
Нет, но вы мне написали, что вы здесь до конца недели.
Я буду здесь до конца недели совершенно.
А потом уедете.
Потом
в Москве когда будете?
в следующий раз.